We went through this process of kind of understanding the problem and understanding optimality. And then we started talking about about verifying that a particular flow is a maximum flow. So first we had to sort of understand what feasible flows were. And last time we talked about verifying optimality. And so far we've been focusing sort of on existential or properties of the problem. And we've only started to touch on algorithms. And so algorithms for maximum flow is going to be the focus of today. But before we go, let me sort of remind you of the sort of the crowning accomplishment of the last lecture, which was this max flow min cut theorem. Which showed the following equivalences. One is that, let's try that again. We wanted characterizations for understanding when a particular flow F is a max flow. And we demonstrated that that happens precisely when we have a feasible flow F. I never actually stated this, but it was implicit in everything that we were doing, that we were only considering feasible flows in our network. So let me just add that here. Equivalents for feasible Fs are that F is a max flow, or that there is no path in the residual graph G sub F, where all the capacities U sub F are changed by the amount of flow on the edge. That was not a question. Okay. Now, as we worked through the proof, this was equivalent to saying that for some cut, or some ST cut in the residual graph is empty. In other words, all of the edges crossing that cut from one side to the other have no capacity, right? And that, from the definition of the residual graph, means that some ST cut has flow equal to capacity. In other words, all of the edges crossing from the S side to the T side are completely saturated by the flow that is going from S to T. Okay. And so we showed that all four of these things were equivalent last time. And so now we have a pretty good understanding of how to check whether a particular flow is maximum. And now we're going to use that to develop algorithms. But are there any questions about where we're coming from before we head into that? No? OK. So we'll keep that around. And so now we're going to ask about finding a maximum flow. But again, I always like to creep up on things. So let's first ask about improving a max flow, or improving a non-maximum flow. So we have at our disposal now a way to say that, OK, you claim this flow is maximum, but it's not a maximum flow. How can we turn that into an algorithm for taking a taking a non-maximum flow and making it into a better, perhaps still not maximum flow? Okay, so what is the way that we demonstrate that a particular flow is not maximal? What do? We find a path called an augmenting path of non-zero capacity edges in the residual graph, right? Why can we do this? And actually, the why kind of goes with how can we do this? What was that? Yeah, how do we find a path in the residual network? BFS, DFS, right? It actually turns out to make a big difference which of these you use. We'll talk about that later. And why do I know that I can find one? Yeah? Right. If I can't find one, it means that my search, my BFS or DFS, gets stopped before I get to T. And so there's some set of vertices that I can reach on this search and others that I cannot reach. That divides the graph into two groups, which define an ST cut. Why is it that I can't reach anything on the other side? Well, because all of the edges crossing to the other side are missing from the residual graph. Why are they missing? Because they're already saturated. So we have a saturated min cut with no capacity in the residual graph, which proves that our flow is maximum. So if our flow is not maximum, then by the contrapositive, there is an augmenting path, and we can find it using this procedure. Right? So we now have an algorithm, an order m time algorithm for demonstrating that a flow is not a maximum flow, right? Or for checking that it is a maximum flow. So now we know how to tell it's maximum or not. If it's not maximum, we want to make it better. How might we do that? Yes?
Well, if you found an augmenting path, just increase the flow on the path.
OK. So to improve, we can add flow to the found augmenting path. Right? How much can we add?
The minimum capacity on the path.
Exactly. So we add an amount equal to the minimum capacity on the path, which saturates that edge. It's now full. It can't take any more flow. And the shorthand for this, I'm going to call this saturating the path. Okay, so when I talk about saturating an augmenting path, I'm saying put as much flow as you possibly can onto that path. Okay? So this gives us an algorithm for improving a flow. Now, how do we go from there to an algorithm for finding a flow? Yeah?
You can keep improving it. And it'll
Great. Yeah, this is a standard, right? We do this all the time. If we have an improvement procedure, we can iterate it until it doesn't work anymore, and then claim that we have something that is best possible, right? So repeat until done. Saturate in augmenting path. So now we have an algorithm that, when it finishes, what can we say when it's done? Yeah?
Not very much.
Not very much. So if it is done, I can't say very much?
Well, you can't necessarily, well, if it's done, then you're done, but you can't necessarily claim that it will finish.
OK, good. So if this is done, we have found a maximum flow. Okay. But there was actually sort of an implicit statement in what you said, which is only conditionally true. You said, when we finish, we have a maximum flow, right? But when do we finish? How do we know if we finish? Okay. That actually takes some thinking. Okay. Yes?
Every step, like, strictly increase the flow across one edge. So
Great. So this is an important piece of any argument, or of many arguments for termination, is that we have a situation where we are continuously improving, right? We never get stuck at a particular value. Each of these augmenting path steps is going to increase the value of the flow. Combined with that, we know that there is a maximum flow value, right? So if you are continually increasing, but there is a fixed upper bound beyond which you cannot go, that would seem to suggest that you'll eventually get to the bound, right? No. Why no? Sorry, a second row.
You could have something like 1 plus 1 half plus 1 4.
Ooh, so we have to worry about limits and things, right? But you know my aversion to calculus, so let's try and stay away from that. Let's consider the special case of integer capacities. Which is always a good, simple special case to begin with. If we have integer capacities on our edges, then can we say something about the termination of this algorithm? Yeah?
you even have to assume integer capacities because we have a finite number of edges and nodes, right?
That's true.
So also, you don't necessarily know that you'll stop by the argument that they're basically constantly increasing, but you don't know that it'll stop at the maximum. So
I will actually, let's poke at that a little bit, because I think we can invert what you said. You said that you know you'll stop, but you don't know that you'll stop that when you stop, you're at the maximum. So I will question both of those statements. Okay? So do I know that I'll stop? That's actually going to take some work. We're going to have to look at that. Okay? There's a reason one might think you'll stop, which is not true, but we'll get to that. And the other is claiming that if you stop, do you know you're at the maximum? Yeah, this is exactly what we argued over here, right? If you stop, if there's no augmenting path left, then you have a maximum flow. That's what we proved last time. So really the only question is, do you stop? If so, when do you stop? I said the running time of this whole procedure. So this is hard to answer in the most general case, which is why I want to start by creeping up with integer capacities. So what can we say if we have an integer graph? Yes?
Can you say that each path we augment, we only augment it once, so the number of paths?
That's an interesting claim. So we're working with a finite graph. So we want to argue that there's only a finite number of edges, of paths in this graph, and therefore that you're not going to augment a path more than once. It's an interesting claim. I don't think that it's true in the most general case, and this is actually connected to the sort of previous assertion. Maximum flow and the augmenting path procedure that we're looking at, it's kind of a greedy algorithm, right? It just keeps on adding. But it is not sort of one-directionally greedy. Okay? We can augment flow on an edge, and then a later augmenting path might come along and take flow off of that edge. Right? We may augment on a path that goes in the opposite direction along an edge that we already used. So there's no a priori bound on how often we might send flow through a particular edge. We might send it through and then take it off, send it through, take it off. Each time we do that, we are increasing the total flow, but what happens on a single edge is mysterious. And so I can't immediately, I think, draw conclusions about using a path only once. But in the integer case, there are things I can say.
Well, if there are integer capacities, then we can be sure that the max flow is actually an integer number. And we can also be sure that every time we augment, we can augment by an integer number.
Good. So let me focus on the second one. Because again, the second one, the first one, yes, the first one is also true, but I'll focus on the second one. So if we have integer capacities, that implies that we can find an integer augmenting path. Yes? Because after all, and by integer, what I mean by that is an integer capacity augmenting path. In other words, we look at the graph. The path that we have has integer capacity, so the smallest capacity on that path is going to be an integer capacity. So when we saturate that path, we are sending an integer amount of flow along that path. Okay. Now that's true the first time, but we're going to do this over and over again. So what what sort of inductive argument do we have to make? Yes.
So there's some maximum flow, and each time we do the augmenting path, we increase our current flow by at least 1.
So you're assuming something. So that if we can say that, we're done. But right now, I've only talked about the first augmenting path and said that we found an integer augmenting path. What happens next? Yeah?
Residual graph is still an integer.
Good. So after we find an integer augmenting path, the residual graph is still integral. Right? The first residual graph is just the graph we start with. After we do an augmentation by an integer, we still have an integer residual graph, and therefore, yeah? We can do it again, right? So there's actually an inductive argument here that each augmentation that we perform in this graph can be an integer augmentation. Okay? Every single augmentation is by an integer. So what's the consequence of that? As somebody already said in the class, every augmentation increases f by 1. And I'm going to be lazy and use f both to denote the flow and the value of the flow. And you can, if you know Haskell or something, you can do type inference in order to know what I'm talking about. Okay? So we're increasing the flow by at least 1 every time. Right? Now, as was also stated, the maximum flow is an integer. Why do we know that the maximum flow is an integer? It's the easiest way to min cut, right? So the maximum flow is equal to the min cut. And the min cut is some cut with edges crossing it, but all of those edges crossing it have integer capacities. So the max flow is in value an integer. So that implies that we have a finite time to terminate, which is really a very nice first start. I mean, we can get picky about, what polynomial it is and so on and so forth, but that first step of going from infinite time to finite time, that's, quite a bit more substantial. Okay? But now let's get picky. How finite is it? What sort of bound can we place on the value of the maximum flow in order to tell us something about the time to terminate? Yes?
Exponential in the size of the max flow?
The time to terminate is exponential in the size of the max flow. So what do you mean by size?
Well, like the number of bits necessary to represent it.
OK. So this is an important point that we're going to be spending a lot of time on today, is the representation of numbers and values, right? So when we look at a graph and talk about the max flow in the graph, and we look at the edges and talk about the capacities of the edges, there are numbers on those edges. And we have to represent those numbers. And usually what we'll do is, if we're talking about integers, we will represent an integer number by a number of bits, which is log of the value of the number, right? So we have these sort of two different quantities to think about. There's the number and there's the log of the number. And both of them are relevant to what we're going to be doing. But for starters, for now, let me assert that the number of augmentations is at most the value f of the max flow. Okay. Okay. Now, how long does a single augmentation take? Order m. It's just a breadth first or depth first search. So we can claim our first time bound for max flow as order m times f. Now, as you say, this can be exponential in the size of the numbers that we're dealing with, but at least it's a bound, right? Now, The problem with this bound is that it states the time in terms of something we don't know, namely the value of the max flow. It's nice to state time bounds in terms of things that we do know at the start of the algorithm. So what are some things that we do know? Well, we know the capacities on the edges, right? So let's give a bound that is in terms of the initial edge capacities instead of in terms of this unknown flow value. Yeah? Okay, and what happens when we take an arbitrary cut? What? Yes. Okay, so any cut in the graph gives us a bound on the maximum flow. So if we just pick some cut and look at the value on the cut, that gives us a bound on the maximum flow value. So if we let U be equal to the max edge capacity, this is a standard notation, capital U as the max edge capacity. How can we use that to state a bound on the maximum flow? Yes?
That multiplied by the number of edges?
That multiplied by the number of edges, right? So if one edge has maximum capacity, has capacity U, that means that the maximum cut capacity is at most m times U, right? Because a cut can only have every edge cross at once. And so that gives us a bound on the maximum flow, right? So the maximum flow value is less than m times U, which implies that our runtime is order of m squared times capital U. Okay. So this is, of course, a much sloppier bound than order m times f, but it's a simply stated bound in terms of the quantities we have at hand at the beginning of running the algorithm. Yes?
Is it also true that the max cut capacity is less than or equal to x and u because it's like cut s?
Yes, so that depends on whether we are considering a graph that is so-called a simple graph, one where there's only one edge between any pair of vertices, or whether we allow a general graph which may actually have multiple parallel edges between pairs of vertices. Now you might ask, why would we want to make the graph more complicated by having multiple parallel edges? Well, this becomes relevant, for example, when we're looking at min-cost flow, which we'll do on Friday or Monday. Yes?
It's also true that it's like bounded by the sum of all the edge weights.
Yes.
Right? And that's something that like is exact because there are also graphs that achieve that.
Yeah, well, so that is exact in the sense that there are graphs where the value of the flow is equal to the sum of the edge weights, but it's not always exact. That is, in some graphs, the flow value may be much less than the sum of the edge weights. Okay, so I'll just add an annotation here that this is NU in simple graphs. Okay. But basically, there's a trade-off between how many quibbles and conditions you want to put on things and how tight you bound the result, right? So MF is tighter than all of these. MF is, in a sense, exact, right? And all of these other ones are sloppier bounds that take less work. Now, how good is that bound? Well, we now have this problem because as we said before, you use a logarithmic number of bits to represent a number. So even really big numbers can be represented using a relatively small number of bits. Right? Now, traditionally, when we talk about polynomial algorithms, is in the size of the input. Right? And if we use this standard way of representing numbers, right, where a number of value 2 to the k only takes k bits, then order m times f is not, or let me use the other bound we showed, m squared u is not polynomial in the size of the inputs. Instead, it is polynomial in the value of the inputs, right? Which is a much weaker condition. So this type of bound is known as a pseudo-polynomial bound. And it can be useful. So in a lot of applications, you actually work with a graph that has only unit capacities, right? A so-called unweighted graph. In an unweighted graph, this type of pseudo-polynomial bound is just fine, right? You have an order m squared running time. It is truly polynomial. But it's something for you to worry about if you're dealing with graphs that have capacities, weighted graphs with numbers on them. Okay? Now to think some more about how that makes things complicated, let's try generalizing this argument to rational numbers. Oh, sorry, before I do that, we accidentally proved something very important, which is the flow integrality theorem. Which says that if the edge capacities are integral, then there exists an integral max flow. A flow where all the flows on edges are in fact integers. Okay. It doesn't say that every maximum flow is integral. You can certainly, in many graphs, construct a max flow where there are fractional values on some edges. But there always is one that's integral, and that's going to have some useful consequences later. Okay. But now let's talk about rationals. So if we run this augmenting path algorithm in a graph with rational edge weights, can we say anything at all? Yes? Terminates in finite time. Which, again, is sort of the biggest, the most important first claim to make. Why do we know that it terminates in finite time? Yes, I'm back.
You can multiply all the capacities by the LCM,
Good. So if we multiply by the least common multiple of all the denominators, or if we're lazy and don't want to compute a least common multiple, we could just multiply by all the denominators, right? Well, no, it actually isn't any worse for the purposes that we're looking at. Then what we get is an integer graph. And we can think about all of our calculations, all of the augmenting paths that we find as running in this integer graph, right? And we just need to scale back down to the original graph. And we know that in this scaled graph, we terminate in finite time, and therefore in the original graph we are also terminating in finite time, because there's an exact correspondence between what's happening in the two graphs. But how finite is that time? Yes?
In one case, if you take large denominator, then you can think of it as adding 1 over, instead of adding 1 at a time, you're adding 1 over that value.
Yes. So if you think about the simulation, what we're sort of doing is, what we could do is work with the original graph, but just argue that there's some minimum quantity, namely 1 over the product of all the denominators, by which we increase the flow in every time step. Right? So the flow increases by 1 over all of the denominators. And the largest possible flow is the sum of all of the numbers, which also has a 1 over the smallest denominator in it, right? So this is finite, but it's not even pseudo-polynomial. I mean, it's not clear how one would define pseudo-polynomial on rational numbers. Right? There's a question of the representation and what the size, is a half a big number or a small number? It sort of depends on your perspective. But we we do have finiteness for rational numbers, so we have an algorithm. What about real numbers? So now we've left computer science behind because we can't actually write down a real number, right? But it's still a fun thing to think about. So imagine that you had a real number RAM where you could actually store and load real numbers in constant time and multiply and add real numbers in constant time. It turns out that this is an insanely powerful machine if you abuse it, because you can basically store the answer to an entire computation, like all the prime numbers. You can just create a real number that has them all in it, right? And then you can look it up in constant time and stuff. But we won't go there. If you use this real number RAM in the way that it is intended to be used, right, and namely you find augmenting paths based on these real numbers, what can we say about this augmenting paths algorithm? Yeah? Maybe infinite. I'm not asking what we can guess. I'm asking what we can say. Well, may not terminate. Even worse, there exist limiting computations, right? You do these saturating augmenting. So in every step, you find an augmenting path and you saturate it. But the limit is not a max flow. So you converge to something suboptimal. Okay? And that's a fun thing to prove, even though it has no practical significance since we never actually work with real numbers. But if you're working with rationals and you're not careful, you may find yourself in a situation that is close to this. And that would be really bad. Okay? So that's our first algorithm, is one that takes any old augmenting path and saturates it. And this works OK for integers, very badly for rational numbers. Right? Yes?
For the bound that bounds for U-bound units that are bound and basically the source still.
Yes, so that's what I was saying. There are all sorts of sort of tighter bounds you can state, right? So the set of edges leaving the source is a cut that bounds the capacity. The sum of all the edges in the graph is a bound. You know, any particular cut that you choose provides a bound. M squared U is one that can be stated just in terms of a simple parameter of the problem, and that's what makes it appealing. Okay. Other questions? All right, so let's try and improve things a little bit. So what we said is that if you find any old augmenting path and augment on it, then that gives you an algorithm. So if we wanted to get a better algorithm, what would be a natural thing to try? Where might we want to be more careful in the, I mean, we've specified a very generic algorithm here, right? Find an augmenting path and augment. Could we enhance it in some way? Yeah. Pick your path more carefully. That seems like a very good idea, right? We've got too much freedom here in the algorithm that we specified. So what might be a more careful, a more targeted way to pick an augmenting path in an effort to get a good algorithm?
Pick the one that has the largest saturated value.
Good. So this is the natural next step, which is to consider the maximum capacity augmenting path algorithm. Right? Can we find a maximum capacity augmenting path? Before, if we want to consider it, we'd better be able to find it. Yeah?
Isn't that just going to be the longest path in the array government?
Yeah?
We don't need to find the maximum path. We need to find a good approximation of the maximum path.
OK, so maybe we sacrifice exactness and settle for an approximation. We actually don't have to. We can find a maximum capacity augmenting path. What is the capacity of a path? It's the minimum edge on the path. right? So does this remind you of anything? Trying to maximize the minimum value on a path? Suppose that I just told you I wanted to, not a path, but a spanning tree, where I maximize the minimum value. Does that remind you of anything? Yeah?
We can do binary search at the minimum.
Okay, so yes, we can guess the minimum value of the maximum value of the minimum, right? And we can use a binary search and say, is there a path where every edge has value greater than k? Okay, if there is, then I'll increase my guess for k. If there isn't, then I'll decrease my guess for k, and I'll use this sort of binary search to home in on the exact value of the maximum capacity path, right? We don't even have to do that. Okay. If you think about the shortest path problem, this is actually an easier problem than the shortest path problem. In shortest paths, you're trying to minimize the sum of the values on the path from S to T, right? Here, you just want to minimize the maximum value on the path from S to T. And max is an easier quantity than sum to work with. Yeah? Good. So this is sort of like the binary search version of the problem, that you can just look at sets of edges, right? So let me consider only the very big edges. Is there a path? No. Okay, I'll add some smaller edges. I'll keep adding smaller edges until I get a path. You can add them one at a time, right? This is more expensive, so you can add them in a binary search fashion, where you take half of the remaining edges and add them and see if you need them all. Okay? But in fact, a small variant on Dijkstra's algorithm, or prim, can find this path. Right? If you think about how Prim's algorithm is building a minimum spanning tree, right? We generally think about Prim's algorithm for undirected graphs, right? Or we just add edges coming out. But you can run Prim's algorithm on a directed graph, where the connection is for edges. You're growing a tree, and you're looking at the edges leaving the tree, right? And so the label on a vertex that you haven't added yet is just equal to the maximum value, to the minimum value on the path to that edge. And you use the standard greedy approach. Take the edge that has the best value, take the vertex that has the best value, incorporate it into the set that you're growing, keep doing this until you reach T. Okay? So there are many ways to do this. Binary search on value, on edges, Prim's or Dijkstra's algorithm. You can do it in order m time pretty easily. But I'll leave the details to you to figure out. Actually, maybe I should be careful and put in order m plus n. Okay. But now that we have it, can we argue that it's a good idea to look for it? How can we assert that finding a max capacity augmenting path is going to be any better than just finding any old augmenting path? Well, if we think about the way we've been analyzing so far, we've been looking at sort of progress, right? There's this optimum, there's this maximum value, and we've been saying that the augmenting path takes us towards the maximum value. Well, if we want to argue that this algorithm is better, then the natural way to do that is to argue that these maximum augmenting path takes us towards the maximum value in big steps, right? That we make a lot of progress when we find a maximum augmenting path. So what we want is an argument that a maximum augmenting path, say, finds a substantial part of what remains to be found. Okay. So in particular, if we can prove, we want to claim that the maximum augmenting path makes significant progress. And the way that we're going to prove that is by proving that there exists an augmenting path that makes large progress. Right? If there exists an augmenting path that goes far, then surely the maximum augmenting path will work well. So we need to show that there is some augmenting path that has a lot of capacity. If we can do that, we're done. So if all we know is that we have this flow yet to be computed, how can we argue that there is some path in that flow that has a lot of flow on it, that has a lot of capacity left? Well, we're just going to go back to our decomposition. Okay? So let's consider the residual graph. Okay? We found a flow so far. Okay? And the residual graph has, let's call it f prime flow yet to be found. Actually, let's not go to the residual graph yet. Let's just look at the original graph. So we have this original graph, and it has flow f. Now we're going to start by finding the maximum capacity path in the original graph. I want to argue that that path has a lot of flow on it, has a lot of capacity. How can I do that? Well, what do we know about flows? We know that they can be decomposed. Right? So we proved last time that you can take a flow and decompose it into flow paths. How many flow paths? Anybody remember? Yeah?
Same number as the number of cuts.
It's not related to the number of cuts. It's actually a lot better than that. It's the number of edges, right? So we can decompose into at most m paths. Right? Because when we did that decomposition, right, each time we took out a path, we were taking out all of the flow from one edge. So we could only do that m times. Right? So if we can decompose a flow, any flow, into m paths, what can we say about the flow on those paths? Yeah?
There's at least one path that has f over n.
Right. So some flow, or some path, has f over m flow on it. But of course, that implies that it has f over m capacity. Right? So that tells us that if we find the max augmenting path, we will find at least f over m flow. Right? And this is not a machine learning class. So remember, this is max augmenting path. Okay? So max augmenting path finds f over m flow. Okay. I claim that's pretty much all we need. Okay. So can somebody complete the analysis? So let me expand this by saying that the residual flow decreases from f to f minus f over m, which I can write as 1 minus 1 over m times f. Okay. That's what happens when we find that first augmenting path. What happens next? Yes?
So instead of doing it f times, you only have to do it m times before you get up to the max flow path?
Well, let's be careful. So it would be nice if every time we found a maximum, every time we did a maximum augmenting path, we found a flow of value f over m, where f is the value of the max flow. That's not quite true. Why isn't that true? Yeah?
F is the value of the current flow in the graph. Which
Good.
is going to be log n.
Good. So basically, we can generalize this argument and say that if the residual flow is f prime, then the flow decomposition tells us that we can find a flow of value 1 minus 1 over m times, a value f prime over m. So the new residual flow is 1 minus 1 over m times f prime. So basically, each time we do a maximum augmenting path calculation, it decreases the flow by a multiplicative factor of 1 minus 1 over m. Okay. So what that tells us is that after k max augmenting paths, the residual flow is 1 minus 1 over m to the k power times f. Now, how can we turn that into time bounds? Well, we're going to break it apart just as we did before. Let's talk first about integers. So if we have a graph with integer capacities, what can we say about the value of, about the runtime of this algorithm? Yes?
It will stop when that geometric progression means that the residual is less than 1.
Good. So the key observation is that if 1 minus 1 over m, or sorry, if the residual flow is less than 1, then it must be 0. This is something we're going to use several times in this class. This fact that when you're working with integers, there's nothing between 0 and 1. So all you have to do is get things below 1, and you've reached 0. Okay? We used it in the Markov inequality when we were talking about hashing, right? So in particular, we were done when 1 minus 1 over m to the k times f is less than 1. All right? And so now if we do some mathematical manipulation, we discover that we need to have k equal to f. I can't do math. Let's see. M log of f, I believe, is the correct value. Okay. Or let me put an order here. Okay. Anybody want to disagree with my math? I'm quite likely wrong, but I think. What's the base? Well, that's why I put an O. Right? Then I don't have to figure it out. I think it's actually a natural log, but we don't care. Okay? Good. So now we have a runtime. And what's interesting about this runtime is that now we can say, well, what's the value of the flow? Well, we said before, this is at most m times u, right? So we can say that our runtime, we have to do this many max augmenting paths. Each of them takes us about order m time. I'm not going to worry about the n log n. Takes us about order m time. And the value of the flow that we start with is m times u. So we can say that our runtime is order m squared log of m times u. Right? Now what's great about that is that we're now talking about the log of the largest capacity. Right? And that is precisely the number of bits that you need to write down the capacity. So now we do have an algorithm which is polynomial in the input size. So this was the first polynomial time algorithm for maximum flow. Okay? It is polynomial in the number of bits that are used to write down the numbers that go with the edge capacities. Yes? So basically you can think of it as a variant on Dijkstra's algorithm. Okay, so there's a lot of ways to do that. One is, so remember, we want to maximize the minimum capacity on the path. So, sorry, I just want to do this in the shortest possible fashion. So suppose that what I did was I set the length of edge E equal to some giant number k raised to the power of minus the capacity of E. Okay? So what does this mean? Since I am taking a negative exponent of a giant number any large capacities are going to be basically 0. And so if you imagine summing the lengths of edges on a path, it's going to be determined by the smallest capacity on the path. Right? Because that's going to dominate in this exponentiation. Okay? So the length of the path is going to be determined by the smallest edge on the path. So if I just find the shortest path in this graph, I'm basically going to be finding the path whose minimum capacity is the largest. All right, so anybody who wants more details can come see me after class. You can, like I said, there's also these binary search methods, and basically, it's an easier problem than the shortest path problem. It just feels harder because you haven't thought about it before. Okay, but working with maximizing the minimum capacity is easier than summing the capacities on the path. Okay. All right, so let's now ask about rationals. Right? We had a good answer for integers, but what about rational numbers? Yes? Okay, so now imagine we multiply out all the denominators, right, by the least common multiple. And so now we have an integer problem. Right? This hasn't changed anything that's going to happen in the algorithm. Right? But now our integer bound applies, right? But it applies actually in a really nice way. So now we have order m squared log of m times the product of all the denominators. Right? I guess times u. Okay. How big is that number? Well, this is something that's going to become a lot clearer when that we're going to go over again when we look at linear programming and various sort of numeric issues. But notice that when you take a product of numbers, the number of bits needed adds. Right? So if you have, in this case, m k-bit numbers, then when I multiply them all together, I'm going to get an m times k-bit number. Right? So here we have mk bits. Okay? Or sorry, yeah, where k is the number of bits that were in my basic numbers. So actually what I should say is m log u bits. And so that's a number, it's a big number, but the log of that number has value m times log of u. So because we're taking the log of this number, we get a polynomial value in the number of bits that were used to write down the numerators and the denominators. So even for rational numbers, you still have an algorithm whose runtime is polynomial in the number of bits that are needed to represent those rational numbers. So it's still a polynomial algorithm for any rationals. Okay. For reals, I'm actually not sure. I suspect that you can prove that its limiting behavior is to find you the maximum flow. But obviously, with reals, you may never actually reach the maximum flow, so you're going to have to study the limits. Okay. All right. So any questions about maximum capacity augmenting path? All right. Then let me show you another algorithm which has pretty much the same runtime, but has a different perspective, which I find very nice for developing algorithms. Actually, before I do that, let's take a little break. Let's take a 2-minute break, stretch, jump up and down, get our energy back. Yes?
Why can't we argue that every time this algorithm runs one cycle, like one edge disappears from the residual graph?
Oh, it does.
So,
the problem is that later it might come back. right? When the edge disappears from the residual graph, it creates a reverse edge, right? And that reverse edge might get used, which will recreate the edge that disappeared.
So there might be two edges going back, and then it might have, okay.
That's what makes this problem so interesting.
Yeah.
It's not monotonic.
Does that mean, wouldn't it be that all Maxwell paths are integral because all Maxwell paths should have the same value?
You mean that all max flows? So the integrality theorem tells you that the value of the maximum flow is an integer.
Right. But wouldn't that
However, there may be many different ways to achieve that value.
okay.
And some of them might allow you to send fractional flow on certain edges.
Oh, okay. So when you say integral Maxwell, you mean every edge?
Every edge has an integer flow on it.
Okay, thanks.
When you do max flow, can you always assume the lower capacity lower weight of all the edges is 0?
No, or rather, sorry. For our version of the problem that we're studying here, we are assuming 0 lower bounds on the edge flows. But in your homework, right, that's saying let's put lower bounds on the edges and find a max flow in that case. That is, sorry, not a max flow, but even the feasibility question: is there a flow that obeys these lower and upper bounds? Is an interesting question. Okay, but it turns out that actually you can solve that one using any standard Maxwell algorithm. There's a transformation that can solve the problem for you. So you don't need to really develop any new technology to handle lower bounds.
It's just that, like, in order to do a Maxwell algorithm or something like this, you need to have a feasible flow first, and then you can prove it.
Well,
feasible.
yeah, feasibility turns out to be feasibility with lower bounds is equivalent to finding max flows. These problems are all each other in disguise, and you'll see some of that in the homework.
Jerry and I have been working on the Fibonacci heaps like randomized.
Yes.
And we think the problem's misstated because if you state it in terms of the size of the heap, then you can get like square root of n time per
A
operation.
lower bound or an upper bound?
Lower bound.
Really?
Whereas
I'd like to see that.
the number of it's logarithmic in the number of, or log squared arithmetic in the number of operations that are performed on the system.
That I once proved, but I thought I had proved it in terms of the number of items. But no, I think you're right. It probably is true that it's on the number of operations. But I haven't seen a lower bound, and I'd be very interested to see that.
Okay. Also, I think we can get slightly better than log squared, like a very, very, very slightly better asymptotic loop than log squared.
Cool. Yeah, there may also be ways to make the algorithm forget its history so that you can turn that log of squared of the number of operations into log squared of number of items. Exactly. Okay, cool. All right, let's get back to work. So in order to continue our break of a sort, I'm going to take a sort of a mental break from these hard algorithms, and let's talk briefly about problem variance. So when I defined the Maxwell problem, I said there's a source, there's a sink. You want to send the maximum flow from the source to the sink. But there are lots of other ways to state the problem that turn out to be no different from the base problem that I've stated. Right? So, for example, you can ask a problem of flow feasibility. Can I send K flow from S to T? Is that question any harder to answer? How would I decide the answer to that feasibility question? Yeah? That takes a little more work, but suppose that I wanted to solve this question, but what I had was a Maxwell algorithm. Could I solve this question? How?
Compute the max flow and compare it to K.
Compute the max flow and compare it to K. right? You're right that you can go the other way too. You can, for example, use binary search on K in order to find the max flow. Let's do something a little bit more interesting. Suppose that I give you multiple sources and sinks. So I label several of the vertices in the network as sources and several of the vertices in the network as sinks. And I ask how much flow you can send in total from all of those sources over to all of the sinks. Can I solve that? Can I transform that into a standard max flow problem? Yes?
You can create a super sink and super.
Good. So for this one, what I do is I take all of my hypothetical sources, my hypothetical sinks. I create a giant super source and a giant super sink. And I now solve the max flow problem from these sources to, from this one source to this one sink. Why is this solving the original problem with the multiple sources and multiple sinks? Yeah? Yes, in fact, I will make it really big. Okay. Now, that can be a problem thinking about the algorithms that we just defined, right? Because their running time is in terms of the maximum capacity. So I shouldn't really put an infinity there. What should I put? Largest egg weight won't suffice. All right, I may want to send all of my flow on this edge. So I'll put an m times u there, and that's good enough. And that doesn't change any of my bounds. Yeah?
Can you just say that you know that they're not going to be the, can you say put infinity though and say you know they're not going to be the min cut?
That's another option, right? But that requires going back to look at the analysis of the algorithm to make sure that you haven't broken anything. This is much, I always prefer laziness, right? So this is the lazy solution. Okay. All right, so why does this work? Well, because obviously, any solution is going to involve flow paths that go from here to here. And so you can just cut off the heads and tails, and you have flow paths that now go from the sources to the sinks. Okay, now that takes us to another variant of the problem where we have explicit supplies and demands. So this is actually the way you would often state a shipment problem, right? So I've got my warehouses over here. I've got my customers over here. Each warehouse has a certain amount of stuff. Each customer wants a certain amount of stuff. How can I send the stuff? Can I get the stuff from the warehouses to the customers without violating any of the transit capacities? So can I solve that using a max flow? If you think about it, we're now back at, it's now a feasibility problem again, right? But now it's feasibility for specific amounts coming from each source and to each sink. Yes?
If you put supernodes like this,
Mm-hmm.
the capacities are just the amount that
Good.
source is producing.
So for this case, I use the same supernode construction, but now instead of creating infinite capacities, I'll put the supplies Si and the demands Di onto the edges as capacities. Once I've done that, how do I now decide if the problem is feasible? Yeah?
You check if the demands are met.
Met by what?
So flow coming from the
What flow? I just created a graph. I don't have a flow yet. Sorry, I'm being pedantic, but what problem do I solve? Yeah?
I find the max flow from the source to T and check if it's equal to some of the others.
Find the ST max flow, and then check if it's equal to the sum of the SIs, which should also be better equal to the sum of the DIs, or there's no solution, right? Or essentially what I'm checking is that I've been able to saturate each of these super edges to provide the supply that is requested and the demands that are requested. Okay? So that problem can be solved using max flow. Here's another one, bipartite matching. This is an interesting algorithmic problem in its own right, where you have two sets of vertices, often called the men and the women, and you have compatibility edges that represent pairs that would do okay on a first date or something like that. Okay. And your goal is, if you have this n graph where you have n vertices on each side, you want to maximize the number of pairings in this graph. Okay, where you want to pair up each thing on the left with something on the right and vice versa, so that each is only paired with a single, because taking 3 people on a first date is always very unpleasant. How can we solve this using MaxFlow? I mean, this arises all the time in various kinds of assignment. So it's a very useful problem to be able to solve. Turns out that all of the algorithms for it are basically MaxFlow algorithms. Yeah?
So to like add like a switch node and a node, give it a capacity of 1 path each.
Exactly. If you think about it, this is just a special case of this problem. Okay? So if, for example, you want to decide if you can perfectly match up everything, okay, then what you're really doing is putting a supply of 1 at each node here and a demand of 1 at each node here. I won't say which are the men and which are the women. And then solving that feasibility problem. Right? So you turn the problem into this kind of graph, and you solve MaxFlow. Now, it turns out, although it's not immediately clear, it's not visible, that you have to make sure that you direct all of these edges from left to right. If you keep these edges undirected, then you solve a different problem. We thought that we had got a really great paper, and then we realized that it wasn't working because we had forgotten to direct these edges. But if you put in directed edges, then you do get a reduction to MaxFlow that allows you to solve this problem. Okay. Let's see. Since you've been so good about asking questions, I'll ask another. I'll point out one other transformation which you may find interesting, which is flows with lower bounds. So you may have thought that this was a different problem, but actually it turns out that it's the same problem. Okay? That is, if you have a MaxFlow algorithm, you can actually solve a flow with lower bounds problem. What was that?
So at least some amount of stuff must flow?
Yes, as stated in the homework, right? So you've got a problem where each edge has some lower bounds, right? So the edges have lower bounds on the flow. What? As well as upper bounds. Yes, lower bounds and upper bounds. Okay. So how do you solve this problem using MaxFlow? Unfortunately not. Right? That doesn't quite work. And I mean, as you push through the homework, you'll see that. But what does work is, step 1, satisfy the lower bounds. All you do is you send an amount of flow equal to each lower bound along the edge that has the lower bound. Okay. Now, what's a little bit weird about that is that you're not sending it from a source to a sink, right? You're sending it from some random vertex to some other random vertex. Okay. So what this is going to do is it's going to create excesses and deficits. On the graph. Right? So if I have a lower bound of 2 on this edge, I'm going to send 2 units of flow from this vertex to this vertex. That means that the tail of the edge is now missing 2 units of flow. It has a hole. And the head of the vertex has 2 extra units of flow that it doesn't want because it's not a source. So how do I correct this imbalance? Right? I have vertices that have flow and don't want it, and I have vertices that are missing flow and want it. What do I do? Yeah?
Supply and demand.
Yeah. So now I use the supply and demand algorithm to send the excesses back to the deficits. Now, I'm not going to fill in the details because then you wouldn't have any fun. And also, this actually, you don't want to use this in order to prove the homework, right? The homework is asking for a sort of an existential argument. You shouldn't have to go through algorithms in order to do it. But if you actually get a lower bound problem and want to solve it, this is how you'll do it. Okay. All right, so now, finishing up today with one more algorithmic concept, which is scaling. So we started thinking about flow by thinking about integers. Okay, but that's actually not the most simple version of the problem. Right? What's even simpler than integers is 0 and 1. Right? So scaling is a way to start by thinking about a 0-1 problem and use the ideas to solve an integer problem. And it shows up all the time in the design of algorithms. There are many scaling algorithms for many different problems. So let's apply this to flow. So how would we solve max flow in a graph with 0-1 capacities? What sort of time bound can we get? This is easier than the problems that we solved, so the answer should be straightforward, right? Yeah?
Just using the first algorithm we did, OM squared.
Yeah, any old augmenting path algorithm, right? If we're just talking about capacity 1 edges, then each augmenting path is exactly what it is. It's a path, right? It sends 1 unit of flow because all of the edges on the path had capacity 1, and so they get saturated and they all disappear. This may create some residual edges. You may get edges with capacity 2 when in the residual graph, but basically you're always going to be looking at 0s, 1s, and 2s on your graph. And so any old augmenting path algorithm will solve this in order m squared time, or in fact in order mn time on a simple graph with no parallel edges, for the simple reason that the maximum value of the flow can only be n because there are only n edges leaving the source. So you only need n augmenting paths. Okay. Now, scaling is a way to get from such an elementary algorithm to an algorithm that works for arbitrary integers. Okay. And we already saw how to transform from rationals to integers, so we can go from rationals to integers to 0, 1. So what's the idea behind scaling? Well, no, that's not what I want. Oh, I know what I mean. So scaling was introduced by Gabo in 1985. But that was only here in the States. It was actually invented in Russia by Dinitz in 73. But unfortunately, all the Russians publish in Russian, and none of the Americans can read Russian, so they often reinvent things that the Russians did a lot sooner. Okay? So the general idea is to apply a 0-1 algorithm to arbitrary integers. And in a sense, it's the opposite of rounding, right? So we know how to round off numbers, right? We take every number and we drop the lowest digit. And now we've simplified the numbers in some way. Well, scaling is the opposite, or is a continuation of that. It says that, well, in order to solve a problem, what you should do is round it in order to make it simpler, solve the simpler problem, and then put back the low order bit that you scaled off. Okay? I'm going to describe it slightly differently, though. But that's sort of the perspective, is that you just round off and then bring back the low order bit. And because you're always just talking about bringing back the low order bit, your algorithms are often as simple as the 0-1 case and avoid some of the numeric complexity of other approaches. So we're going to think of our capacities as log u bit numbers. And what we're going to do is reveal 1 bit at a time. And each time we reveal a bit, we're going to solve the perturbed problem that's created by revealing that bit. Okay. So we're going to start with all the capacity. Actually, let me use a new board. So we're going to start with every number rounded as much as it could possibly be rounded. So what is the sort of extreme rounding of every number in the world? 0. Okay. So we start with everything rounded to 0. Can we find a max flow in that graph? Yes, we already have one. Okay. Now what we're going to do is we're going to shift in the high order bit from every capacity. Okay. So that means that some of the capacities now become 1 because they're bigger than u over 2. All of the other capacities are still 0. Okay. So now we have a graph where we had a max flow, but now we've actually brought in some more capacity, right? We've turned some zeros into non-zero capacities. So we no longer have a max flow. We need to fix the max flow. How do we fix the flow? Yeah? Sure. We use an augmenting path algorithm. Okay. Now again, we're working in this graph where the capacities are integers. As we do many phases, we may shift in more capacity and actually have edge weights that are integers. Okay. But we are working with the integer case. But what we're going to focus on is the one bit that we brought in, and ask how long does it take this augmenting path algorithm to run? Yeah?
Only need to consider the edges that got added in.
OK, so if the edges that it's true, the edges that added in have to play a role, right? If the flow doesn't use them, then nothing is going to change, right? So something has to matter about the edges that got added in. They have presumably created some more capacity in the graph so that we can send some more flow. Okay. So we need to basically use up the new capacity in the residual graph. Right? So how much new capacity might there be in the residual graph? How many augmenting paths might we need to compute in this graph where we've brought in some more capacity? If we didn't know we were scaling, if we just said, here's a graph that has some integer capacities in it, then all we have are the bounds from before, these sort of bounds which are equal to the maximum capacity u. But because we're scaling, we can say something much stronger. Okay? So the key thing to notice is that before the scaling step, we had a max flow. Which, as we saw at the beginning of class, means that the flow saturates some cut. Which is to say that the residual capacity of some cut is 0. Okay? So we had some arbitrary flow, but there's some cut where we had 0 capacity in the residual graph. Now we scale in. So we bring in, what does that scaling in do? Right? So scaling doubles some numbers, doubles the capacities, and then adds 1 to some of them as we reveal the next bit of the scaling algorithm. So when we double the edge capacities, and then turn some of the low order bits to 1, what does that do to the capacity? What does that do to this residual graph? In particular, what does it do to this cut? What can we say is the capacity of this cut after a scaling step? Yes?
It should be the previous max flow plus maybe a couple of ones.
Right. So that's the key, is that these edges had residual capacity 0. Right? So when we double it, it's still 0. But then each may gain 1 from the new bit that gets shifted in. Okay? So each edge crossing this cut has capacity at most 1 after the shift. What does that tell us about the residual flow? Well, a particular edge increases by 1, but we may have many edges crossing this cut. So how much can the total capacity of this cut increase? By m, right? In the worst case, all of the edges are crossing the cut, the min cut. So we get an increase by at most m in the flow value. And that implies that at most m augmentations are needed to find the new max flow. So a single scaling step involves just m augmenting path computations. Each of those augmenting path computations is in a graph where we're not looking for maximum augmenting path, right? We don't need a Dijkstra algorithm, data structures, anything like that. We're just looking for any old augmenting path, because every augmenting path will have value 1. And that's all we rely on. So we find these m augmenting paths. Each takes m time. And that completes a single scaling phase. How many scaling phases are needed? Well, log u, because that's how long it takes us to shift in all the bits from the biggest number. And that means that our overall runtime is order m squared log u. Okay, which is quite similar to the running time for max augmenting path. But once you get your head around this idea of scaling, this is a much simpler algorithm, right? You're not using any data structures now beyond the graph itself and doing a reachability calculation. It's also, it's log u instead of log of m times u, so arguably it's a little bit better, but it's the same sort of algorithm. So as we finish up, let me just point at where we want to go next. We now have algorithms whose running time is polynomial, but it's polynomial in a slightly annoying way because we have to talk about these bit representations of the numbers. What would make an algorithm really polynomial, or sort of polynomial in an ideal sense, is if its runtime does not depend on the values of the numbers. If you could use it even in a real numbered RAM, where the runtime only depended on the size of the graph. And that will be the focus of our attention on Wednesday.